Okay. Good. Okay. So you can turn the video on. Okay, there you go. It's okay. Don't worry. So this Kisel. This is the one. Kisel. Oh my God.
Yes, sir.
हाँ कोई वीडियो करा हाँ नहीं. Okay, so let's do this. So the okay, so let's do this. So last time we did uh, last time we did matrix addition. Okay, and then what we're doing you're kind of defining the addition, but at the same time you're kind of looking at the uh, kind of what are the operations that really needs to define the matrix addition. Okay, so for example, for the matrix addition here, you using the addition in the addition of the coefficients, like the entries, not coefficients, entries. Okay, and let me draw this picture. So matrices. So what we're really after is this one, talking about the algebra of matrices. Let's say n by n, mn over f, where the entries are from f. This f stands for typically real or complex. Okay, when you don't want to specify the you see, they had the beard thing. Looks good. That's good. That's good. Okay, now I see. Okay, so so this is algebra of matrices, and when you don't want to specify whether the entries are real or complex, we put f. Okay, so when you write f, that means it's real or complex, both. Okay, now so the matrices has three operations. Okay, so you have addition, multiplication, and scalar multiplication. Okay, so let me write down this picture. So we have so I mean this is what we are after: mn f, addition, multiplication, and scalar multiplication. Okay, now this is the full structure of for matrices. Okay, and this is called an algebra. Okay, we will show that this is an algebra. Okay, now there are like smaller structures in here. For example, you can ask, what if you consider just the matrices under addition and scalar multiplication? Okay, so if you have those 2, 3. And we are not talking about the multiply matrices, right? So if you have this, and the structure of this thing is going to be an algebra, going to be a vector space. You remember with vectors, you can add them and you can scalar multiply them. You cannot like multiply 2 vectors and get, I mean, there is the cross product, but it's a special case. Okay, good. And now the next thing is, if you just consider matrices, MNF, with addition and multiplication without referring to the scalar multiplication. Okay, so what you have here is a ring, right? And now in here, if you just consider MNF and plus, and if you're only considering the addition, and this one is actually going to be an group. Okay. And actually, since the field F, so this F, R, and C, those are going to be fields, but because the F is actually commutative under addition, okay, so this one is going to be an abelian group. Okay. Now, if you just consider this guy, matrices under multiplication, and so the multiplication is going to be associative. We'll talk about it in a bit, but it's going to be closed, associative, but it will have identity, but we won't have inverse. Okay, so there are some matrices that doesn't have inverse. Okay, so if you just take the matrices under multiplication, it's not going to be a group. It's going to be something smaller than a group. It's going to have like less structure than a group. Okay, so this thing is going to be a monoid. Okay, but inside here, we have, if you do this thing, so if you do this, so instead of like, I mean, what you have done so far, we have kind of reduced the operations and kept the same set. But in here, if you take the, uh, if you, I mean, you cannot reduce the operation because you have only one left. So if you look at only the, if you take the matrices and if you look at the invertible matrices, and you take the invertible matrices and under multiplication, of course, and that would form a group. Okay, and this is a group. And this one is actually non-commutative, non-abelian. Okay. So like what we're trying to do in the first part of the lecture is kind of define like addition, multiplication, scalar multiplication, and then you actually see what the structure is, what kind of the substructure. And this would give us an introduction to the all these basic algebraic structures. Okay, and that's a plan. And let me say a couple more things. And in here there is something interesting. In here, we consider the case Mn instead of taking real or complexes, we just take a ring R as the for the entries, and you'll be able to define addition. And this scalar multiplication would be like you're multiplying by these scalars, but the scalars are coming from a ring. Okay. And if you look at this thing, this would be an example of they call an R module. This is going to be an R module. And basically R module is where it's like a vector space, but the scalars are coming from a ring uh, rather than a field. Okay. And good. And the only thing that we didn't talk about in here is it's like what a field, what's the definition of a field? Field is a ring, but every non-zero element has a multiplicative inverse. Okay, so this would be an example of a field. Good. So any questions about this? Okay. Now, any questions? Kisala? Uh, okay, so let's talk about matrix multiplication. So you have seen this thing, like 2, 3, 1, 1, 4, 2, and multiply this by 1, 2, 1. Okay. So what you do, you kind of take this column and then multiply with this. Okay, so the first entry, you'll get 2 times 1 plus 3 times 3 plus 1 times 1. Okay, and then the second one is going to be you're multiplying this with this. Okay, so that's going to be 2 times 1 plus 3 times 3 plus 1 times 1. Okay, and the next one, this one and this one. It's going to be 2 times 1 plus 3 times 9 plus 1 times 2. Okay. And then you have what goes here is 1 times 1 plus 4 times 3 plus 2 times 1. And then so on and so on. Okay. Kisali, your picture got turned. Now, so this is good, right? Now, I mean, this way of this a funny way of multiplying, but you can ask like why multiply this way, and we can answer that question later. So when we have a define like maps between linear vector space, those would be linear transformations, and they're going to be, you will be able to represent them by matrices. And so we'll get into a situation where have a map T that's from the vector space V to W, and then you have another map S that's going to be W to U, let's say. And if you pick basis for V, W, and U, this matrix T, this linear transformation T can be represented by a matrix, and the linear transformation S can be represented by a matrix, right? And now when you have two maps like this, and you can compute the composition of these two maps, just like the in the case of sets. So this is T composite S. And the matrix of this can be computed using like matrix multiplication. Okay, so the kind of reason like why we multiply matrices this way, that's that for us. But there is a guy called Alan Conan. He's a field medalist, and he created something called non-commutative geometry. And he was telling something, and I met there was a guy who's a postdoc and who's kind of in that family. He was telling like the kind of something along the lines that what really happened, like he rediscovered matrix multiplication. So don't know what it means. Probably means like the he's telling like the matrix multiplication has to. He said that he's telling that there's reasons underneath that justifies the matrices should be multiplied this way. Okay, probably that's deeper than this one. Okay, like more fundamental. Okay, let me say one thing about these things. So there is a story. There's a story about why, like these things seems like very arbitrary, right? You have a bunch of names: algebras, vector space, addition, multiplication, right? And there is a claim that if you have some aliens coming into Earth, okay, they might not have 10 fingers, like stuff like that, but they would have this abstract algebra. Okay, so and you see this thing in even in Yeah, so alien comes to here, if they can come, they should know abstract. I mean, they will know abstract algebra. No. And then there is something similar. Uh, Probably you guys know about, you learned something called object-oriented programming. And there is another one called generic programming or template programming. So in there, like they have something called templates. So it's like not object oriented, but like functional programming, and then they create something called like templates. And templates are like almost uh, like these algebraic structures. They have like different operations uh, and so on, but they don't enforce the properties of the operations. But a template, like for example, like algebra would be a template. Uh, Actually, there is something that if you're doing this, you learn programming, do this. So there is something called Sage. Uh, this is the open source equivalent of Mathematica. And what they're saying, kind of the idea is, if you, I mean, this is different than uh, like different. So the objects in here, they are not numerical, in the sense that if you have a surface, uh, uh, if you're doing something with the surface, typically uh, what happens, you have this thing, and then when you compute anything, you look at the approximation of this. So it have like a bunch of points in here, and because like whenever you do computations, all you're using is these points. And so you'd store this, you will like the actual object that deals with this surface is bunch of points, in like it's programmed that way, okay, typically. But in here, they're done with the actual equation. They are not approximate object, they're like exact objects. So it'll be like really nice to go in Sage and then look at the uh, structure of all the mathematical objects and how they have arranged it. It should be like this. You have the classes, subclasses, and so on and so on. Okay. And if you go in there and look at it, that you would get a much bigger picture than the ones that we have here. Okay. And Sage is a good thing to know. For example, like yeah, you can do yeah uh, you can do computations with like different fields. For example, like instead of this field, you can do like finite fields and so on. Anyway, so that's that. Now let's go back in here. Now let's define the matrix multi. So this is the idea, and then uh, definition. So we have matrix A. Let's say this is Aij m by n, and then matrix B, Bij mn n by k, n by yeah, n by k, n by l. Okay. Now n by Now we define the product A times B, matrix C, and C is going to be C I J M by P, and so it's going to be C I J is going to be, it'll have some formula, okay? So this is the matrix A, this is the matrix B, okay? So we have the ith row. So this is AI1, AI2, dot, 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 AI, this is m by n, so it goes up to n, okay? And in here, so this is, let's say this is B 1, K, B 2K, and it's going to go all the way down to B n K. Okay, so let's get multiplied. Something like this one. It multiplied with this. Okay. And so this is I. You remember this index was J. Okay. And let's use this J here, and this is the kth column. Okay, so it's going to be C C I K. It's going to be, now you're going to be summing over this index J. Okay, so you're multiplying this with this, and this with this, and so on. Okay, so this is going to be AI1 times B1K plus AI2 times B2K plus dot 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 AIN times BNK. Okay, good. Now, so let me write the summation. So CIK is sum J equals 1 up to N A I J B J K. Okay. So we define the matrix multiplication. So can take m by n matrices, and so this is where matrix A coming from, and this is where matrix B coming from, right? So the output is going to be a matrix M by P matrix. Okay. Matrix A. The matrix multiplication is going to be a map from the product of these two sets, and you get here. Okay, now the question for us, so remember, for the matrix addition to be defined, you want the entries to be, if it is a group, then you can define it. Okay, and you didn't even need the group to be abelian. Okay, and if the group is abelian, then the matrices under addition is going to be abelian. Okay, now so can you define the matrix multiplication if the entries are coming just from a group?
The group does have multiplication operations, right?
Hmm?
The group does have multiplication
Yeah,
operations, right?
yeah. So the group just has one operation. Yeah, like the addition.
There's
So
only addition and multiplying, so it's multiplying can't happen.
yeah, so you cannot define it, right? If it is like, if you
Yeah.
look at this formula right here, right? What you need, the entries, you need to be able to multiply, and then you need to be able to add. Okay, good. So what's happening here? So in really, we can define matrix multiplication in this way, where R is a ring. Okay, now you like look back up here, kind of notice that this formula makes sense. I mean, this formula makes sense. If A and B are coming from a ring, you have the two operations, because you'd be adding and multiplying, so you can do this. Okay, Okay, now this is good. Any questions on this? Okay, so let's so next, properties of matrix multiplication. So let's look at the properties. So now, like now you have matrix. You talk about the multiplication. You kind of think about the situation. We already have the addition for the coefficients. Okay. So so matrix addition is kind of is also possible, and have the matrix multiplication. But so when you talk about the properties at this stage, you want to think about properties of the matrix addition by itself, and we have done those. And then you have properties of matrix multiplication by itself, and then you have properties of some compatibility of addition and multiplication. Okay, so for now we are focusing on matrices, but with the just with the multiplication, right? So the if you have a, so let's have a look at this this definition. So you have the definition of a monoid. So it's a set M with the binary operation. Right? Operation, say M and dot, and this that is associative. And as an identity. Right, so that's the definition of monoid. So we can like ask the so the basic question is, we can ask, we take M let's say n by n matrices over a ring under multiplication, it's a monoid. Right, so all I'm trying to get is, if you have a binary operation, so the first thing, something that we really like, is the associativity. Okay. So for a group, we have the closed, associative, identity, and inverse. And so when you look at the closeness is okay. The associativity is the next thing that we're after. Okay. And so it's a good thing to ask this question. So no, but so if you're answering that, let's show that proposition. Matrix multiplication is actually associative. Meaning you can show that we take 3 matrices and you multiply A with B, and then you take the product and then you multiply that with C, and this is same as multiplying the matrix A with the product of B and C. Okay, so that means when you write a product of 3 matrices, you can just write ABC. You don't have to put brackets. Okay, but you cannot write AB equals BA. Okay, so the associativity tells you and you multiply a bunch of things, you don't have to put brackets. Okay, now there is something that that I can skip in here. So see, with the matrix multiplication, like you cannot multiply any two. We can take like you cannot multiply any two different matrices. They have to have this M has to match it this. Sorry, this N has to match it the N here. Okay. So if you're thinking like so in general, like in here, now as these questions I put N by N. So if you have N by N matrices multiplied with N by N matrices, then the product is also going to be N by N. Okay, and so in that case in here this multiplication is going to be like well defined. It's going to produce something in the same set, same type. Okay, but the associative law, as turns out, you can this works with like any as long as you can multiply this, it works. Okay, so
I have a question with the definition of monoid.
mono, yeah.
I have a question with the definition of the monoid.
Uh-huh.
So it says like with the binary operation.
Uh-huh.
So does it mean the binary operation multiplication or addition or both? So
Uh,
yeah,
so this
I'm not very sure with the term binary
yeah.
operation.
So okay, so uh so uh doesn't have, so this general definition, it's about you have a set and this binary operation is defined to be a map. It's just a map. Okay, this thing is actually map M cross M into M. So that means it takes two elements from A and B and it maps to some element. We call it the A dot B. Right? So we are familiar with plus and times, but those are those come from like reals. Okay, and in here, for example, with matrices, you can take matrices. You can think of this operation as the addition. Then it's going to be a monoid, and also we take the multiplication. That thing is also going to be a monoid if the coefficients are like, let's say, reals or complexes. Okay, so when you write this dot, you think of it as just like one operation, right? So we talk about like to so what happens when if you go through the like list of things, you have the monoid and then you have a group, which is nice, it has inverses, and then the next one is rings, and the rings has two operations, and we typically denote them by addition and multiplication. And the addition for a ring, and we also assume that the addition is abelian. Group part is abelian, and then there is a multiplication. And okay, so we keep using those addition and multiplication from reals, but in general, these don't have to be. Okay,
Yeah,
Aditya.
so what you mean is you take some two things and do an binary operation, then you should get it from the same the family from the
Same
input.
set, yeah,
So like that, no. So
yeah, yeah.
so yeah. So if I say uh, let's say I'm taking integers, okay. If I
Uh-huh.
divide it, I won't probably won't get a. I can get, but I won't. Sometimes I won't get a integer, no, so it can't be a binary operation, something like that.
Exactly. Yeah, yeah.
Uh,
Division is not a binary operation on integers.
okay. So addition can be an binary operation.
Hmm?
By addition is an binary operation.
Yeah, addition is a binary operation on integers.
So okay, let's say since monoid has only one binary operation,
Uh-huh.
how can there be associativity when there's only when I don't know if you can prove that associativity addition.
Uh, uh, so the associativity property, uh, it's a property about it's a property about one operation. See, is okay.
So okay, I'm not sure.
Uh, so okay, so the So what's happening? We started, so we got the kind of idea or like intuition from real numbers, right? Real numbers, complex numbers, matrices, and vectors. Those are the things that we know from A levels, high school, right? And we use those things to uh, motivate like these different algebraic structures. Okay, so what's happening? So for algebra, for example, it's a set, some set A with two binary operations and a scalar multiplication. Okay, and the matrices are going to be just one example of an algebra. Okay, so for example, let me give you a totally different example for algebra. Example. Let's consider this set A, which is functions from say 0, 1 interval uh, into complex numbers. Okay, so 0, 1 interval is just the set this guy, 0 and 1. Okay, now in here we can define f plus g. We have like two elements from the set A, and then we can define addition. Okay, so addition of two function is going to be defined by this function. Okay, and then we can define the multiplication of two functions, and you define it this way. Good, and we take some lambda complex numbers, then you can define this guy lambda times f. You can define scalar multiplication on A. So the lambda times f is going to be this new function, which is defined by this. Okay, so A together with plus, let me write this thing as multiplication. Plus, and this dot is an algebra. Algebra OC. Typically, we mention the where the scalars are coming from. Okay. And actually, in this case, you can show that actually this thing is commutative. Meaning that f times g is equal to g times f. Good? So let me make this thing the exercise one. show that this A plus cross dot is commutative. Oh, like verify all the properties. Okay. Does this answer your question?
Previous question, like how addition becomes associative.
So you asked if the addition is associative?
Yeah, I got the answer when I said it out loud.
Yeah, it is associative.
Yeah,
Yeah. Oh, that was the question. Okay. Matrix addition is associative. Right? And I think we proved it last time. Okay. Yeah, this was easy because the formula was simple, but the multiplication is going to be trouble. Okay, but even though we say like addition and multiplication, we are not referring to the addition and multiplication from the reals, right? So you like overuse it, but yeah. See, like this is again like a very odd thing to do because typically you don't get introduced to all these things, right? Typically you like learn about like groups for a semester, and then you see the definition of the ring and then the definition of a field, and you do linear algebra. So like you kind of go through one you define something and you learn about it for a semester, and then you see the definition of the next thing. Right? So like I want you to, I don't expect to be like, I mean, it's going to take some time to get used to this language, but it's a language. Okay. And yeah, exactly. Typically what yeah, you do is you just like learn about groups, and that's it. And literally you won't see the definition of a ring for a long time. Okay. But this, I mean, it's not like, we have good examples. We have the matrices, that's algebra. And like everything you see here is just substructures of algebra. Okay. So, okay. Now let's go back here. So the proposition is matrix multiplication is associative. So in here, let's say A is a matrix Aij m by n. B is a matrix Bij n by p, and C is a matrix Cij p by q. Okay. Now so the A times B makes sense. You can multiply matrix A by B because m equals, sorry, this n equals 1 here, right? And then once you multiply these two, what you get here is M by P matrix, right? And the matrix C is P by Q. So when you multiply these two matrices, you will get M by Q matrix. Okay. Now, if you multiply matrices B and C, you'll get N by Q matrix. Okay. And when you multiply that N by Q matrix with M by N matrix, so you'll get M by Q. Okay. So the left-hand side and the right-hand side both would ultimately produce a matrix with M by Q matrix. Okay. So let's write down the so we have A B. I want to show that this is equal to. Right, so you take a element from here. So let's call this matrix D. Let's call this matrix E. Right, so the ijth element of the matrix D is going to be sum. So this matrix is M by N, N by P, and this one is P by Q. So what happens? We're going to be summing over this this P. Okay, you remember that was the formula. J goes from 1 up to N. Okay. So let's put a dummy variable. K equals 1 up to P. Ikth entry of A times B, and you have to multiply that with the kjth entry of the matrix C. Okay. Now the ikth entry of the matrix AB is simply, so this is going to be sum L equals, so this is a matrix M by N, and it's a matrix N by P, right? So you'd be summing over N, like 1 up to N, A I L B L K, okay, times C. Okay. I mean, this type of things. like following your nose now. So in here, what we are after, so this is m by n, and this one is going to be n by q, right? So you want to make the in the right hand side, you want the summation that goes up to n terms to be in the outside, and you want the other one to be inside. Okay, so we want to switch these summations. Okay, so that can be done. So so we go here. Okay, 1 up to p, and multiply okay. Okay. So don't bring the ckj to the other side. Okay. So don't write this in front here. So I mean, you can do it, but you can do it if you know that the entry is coming from a ring that where the ring is commutative. Okay, so the multiplication that's happening inside is the multiplication in here. Okay, good. So go back here. And we don't have to worry about these brackets, and we can move it around easily because the rings are associative property. Okay. Now we switch these summations. Uh, the reason for that, I mean, this is a double sum. We have like huge. If you expand it, you get like a huge sum. But it's like a whole bunch of pluses, and these elements are coming from a ring, and then the ring is what? It's commutative and addition. It's abelian. Okay, so you can rearrange the terms. A plus b equals b plus a, and you can do like a lot of. Okay, so that's what's happening in here. Okay. So now L equals 1 up to n. We can pull out this A, I, L. Then you go here. Okay. So this is so you can go in and you see a computer. This is okay, totally okay. You see a computation first. We kind of think of it as these entries as like real, so like complex numbers, right? And then you like again think again, and then you go like, okay, this works for a ring, right? Good. So good. Now, so let me finish this thing and come back to this thing. So we have sum L equals 1 up to n, A, I, L, and this one is the LKth entry of, LJth entry of the matrix B times C. Okay. And now this summation will give you the ijth entry of A times B. That's like E ij. Yeah, I call this matrix E. Okay, that's ijth entry of. So what we have shown that the ijth entry of the matrix D is same as the ijth entry of the matrix E. Okay, so the matrix D and E, they have the same entries. Okay, so that means matrix D is equal to matrix E. Okay, so the matrix multiplication is associative. Good. Now, so let's go back in here. So there is something that we missed. Okay. Let's go and look at these two steps here. And okay. So what's happening here? So we have a sum inside, and you have multiplying from something outside, and then you kind of remove the bracket by multiplying from the right hand side. Okay, so what we're using, we call this thing star. We call this thing double star. So the star is the bigger version of this property. Okay. And double star is actually going from here, have this thing times a sum, and then you bring this thing inside. Okay. So the double star is a version of this. Okay. And so these things are called distributive properties. Okay. So now if you go back to let's go back to the so if so the star is actually using this distributive property, but like with like n terms, right? Because you have not n terms. And if you have this property, you can use the induction to prove something like that easily. Okay, but so we've been like saying this: the entries have to have like for the matrix multiplication to be defined, we want the entries to be from a ring, right? And we have seen that we need the addition to be commutative. For example, when we switch terms in here, we use that here. Okay. And we have used these guys here, like changing the brackets. Right. So this would be the fact that multiplication is associative. We haven't used that. I mean, we don't require that ring would have an identity multiplicative, but we require that ring has these distributive properties. Okay. Good. So let me write down the full definition of a ring. This is kind of crazy, but it's like you are like kind of proving these things, but gets the motivation, and then you kind of understand what's really needed for the proof is these properties and have a name for it. Okay, so you get introduced to these things too. So the definition for ring. Okay, so this is a set R with two operations. And we call them plus and time. Okay. And this they don't have to be like, I mean, this ring is not reals. Okay. And we want R comma plus to be an abelian group. Okay. and we want this multiplication is associative. Uh, not not necessarily with identity. So the rings typically, typically when we consider rings, those rings would have identity, but the actual definition doesn't require that the rings have identity. Okay, and then you have this distributive laws. Okay. Star and double star holds for all A, B, and C. Good. Any question? Okay, now it is the exercise 2. Write this thing very carefully, okay? Carefully. Exercise 2. Let R be a ring. Show that n by n matrices over R is a ring. Okay. So typically, let R be a ring. And also if R as an identity, for multiplication. Okay. When you mention that a ring has identity, because we know that always the addition has identity, right? So if R has an identity, then this one also has an identity. Right? In other words, if the ring R has identity, then actually then this thing is true. It's going to be a monoid because it's associative. We already proved that, and then it's going to have a identity if ring ring R has an identity. Okay. So the answer to this question is yes, if R has an identity. This E stands for the identity. Okay. Good. Let's take a little break. Is that okay? Break for like 10 minutes.
So there's I have a more problem. Do I have to show that there's also an additive identity? Zero.
Say it again. Say it again. Ask the question.
So in a ring, I have to, there's addition as well as multiplication now.
Uh-huh.
So to show that M is a ring, that matrix M is a ring, I have to show that no, it's saying like if I had to show that it has a an identity, the element, I have to show that M into E is M, and do I have to show that M plus 0 equals M?
Oh, so that one we did already. So
Oh,
we did that with the addition part.
yeah.
Okay, so we
So no
don't
need
have
to show
to
the
do
0
that
thing.
part. Yeah. So for this one, you can just assume that the matrices are actually abelian group, because the ring has addition and that addition is abelian. So that means like last time we proved that the matrices are going to be abelian under addition, commutative under addition. Now you're adding so what you're really doing, you're going along, some path like this, you're going here. So you're getting to matrices and you're going this way. Okay, so you're proving that this is an abelian group, and now you're proving that this is a ring. And next, we'll show that this is an algebra. Okay, good, good. Yeah, any other questions? Let me pause the recording. Okay, so okay, so let's I mean uh, the way, I mean, when you look at these objects in this way. So, for example, if R is a ring, then We can talk about this like M by N matrices with entries coming from M by M, N by N. Okay. Because what's inside here is a ring. R is a ring, so this is a ring. And you can define matrices over elements in a ring. Okay? You let me write let me do this one. I mean, I gave the similar exercise last time. So if this ring has identity, it's an identity, then R has an identity. Okay. I mean, typically call it a ring with when it comes to multiplicative identity, we call it the unit. So if this kind of normal way of writing this thing would be, if this thing is ring with unity, then the R itself is a ring with unity. Okay, good. Now, so finally, let's define scale multiplication. So if we have scale, so let's say this is lambda field F, and then you have matrix A, M by N matrix with entries from F, then lambda times F, lambda times A, the ijth entry is simply lambda times Aij. Okay? And so exercise 4, show that let's say N by N matrices with entries from F, which is F stands for real or complex, is an algebra. Okay, so there are properties that are specific to like scalars, for example, the scalar multiplication. There are properties like lambda 1 times lambda 2 A equals lambda 1 times lambda 2a, and so on. There are things like this that are purely about the scalars, and then you have like properties that interacts with the addition, and there are properties that interacts with the multiplication. Okay. But this is not the full list, okay? So looking here for the full list. Now, let's go back up here. So we have seen examples of these guys, and we will study this thing like very detailed. Okay. Talked about this. Now, let's go in here. Okay, so now we know about the matrix multiplication. Let's go back and look at this and like the row reduction. Okay, so let's have a look at that. What happened in detail. So I'd like to typically like doing a linear algebra, not like done right, but like the normal way. You do a lot of matrices stuff. Okay, instead of playing vector spaces, and you would start with the systems of linear equations and so on. Yeah, let's do kind of that part too. But I have used matrices to introduce these even other structures. Okay, so let's go back. Go back to this. So this is the part 2 of the lecture. Solving systems of linear equation. Group actions on a set. Okay, so the first one, now that we have any questions, Aditya? Questions? Okay. So now that we have the notation for matrix multiplication, we can write down the system. So M by N system, linear equations. Okay, so this is the format of the m by n system of linear equations. Okay, it's m variable. M equations and n variables. Okay, and this side can be written this way. In this equation, you can write it this way: b1, b2, dot dot dot, bm. Okay, and in here, x1, x2, dot dot dot, xn. Okay, and then here you have a11, a12. Okay, and if you multiply these two matrices, so this is, let's call this thing matrix A, and let's call this matrix X. Let's call this one B. Okay, so the system can be written this way: Ax equals B. Okay, so now let's look at the row operations. So matrix multiplication. And row operations. Okay, so let's now so when we did row operations, we changed the system. So that means what you notice that what happens, you're changing the matrix A. Okay, and also this matrix B. Okay, now let's try out some of these examples. Let's take this matrix m by m, and that's my m by n matrix. We have this all ones. Okay, and this one is called the matrix im. We multiply A with the identity matrix, nothing is going to happen. Okay, and actually this im is the multiplicative identity for matrices. Okay, and remember, in general, in order to be able to write this thing, this one is coming from the this one is like the multiplicative identity in the ring, so need to have this thing to be able to do it. Okay, so okay, so we know that so if you multiply matrix with the IM, you'll get back this. So IM times A would be equal to A. Okay. Even when A is M by N matrix rather than M by M. Okay. It will still give you the same matrix. Now, let's try out this. So the first row operation was to switch row I with row J. Okay, so we wrote it like Ri get switched with Rj. Now, let's say this is the ith row and this is the jth one. You take the identity matrix and if you want to switch the ith row and jth row, you switch the ith row and jth row of the identity matrix. You create, so you get a matrix that looks like this. Okay. And if you multiply this thing with the matrix A, so this has, call this thing the row 1, row 2, and so on, in rows. If you multiply this way, you will get this guy. Row 1, and you have the, in the place where, see the, when you get row I, to get row I, so what you're doing typically, in the case of the identity matrix, you have I here, and this side is gonna hit here, right? This is, but if we move it to here, that's gonna hit a different row. Okay, so you're gonna multiply things in there. So this, what you get switched row I and row J. So you get row J here and row I here. Call it row I here, row J here. Okay. And good. Now, and then the third one, we call this thing the 0th one. Okay, so the first one, the second one. Second one is you take ith row and then you replace it by lambda times the ith row, lambda not equal to 0. Okay, that was like multiplying by a scalar. We typically want to be able to get rid of a coefficient and you get like 1. Okay, and so this can be done by multiplying by a matrix. So we have the ith row here, and then you multiply it. Instead of 1, you put lambda. Right, when you multiply with this, you have matrix A here. You get, again, the first row stays the same, but ith row would be turned into lambda I. Okay. So this row operation can be done using like multiplying by a matrix like this. Okay. Now, the third one is Ri get replaced by Ri times C times Rj. So this can be done by multiplying the matrix like this. So we have all the identities, all the ones in the diagonal. Let's say this is I and this is J. So when you multiply with this, so you remember when you multiply, you get this row and this goes in here. And when you have 1, that's going to pick up this row. Okay. And that's going to put it back into the ith row. But if you want to pick up a multiple of jth row, what you do, you put a C here. So if you put a C here, then when you multiply, you're not only multiplying these entries, but you'll be multiplying these ones too. Everything get multiplied by C. Okay. So if you create a matrix like this with the C here, and multiply with this, so we have R1, Ri, then Rj. If you multiply with this matrix, you will end up with R1 and Ri. Oh, so in the Ri1 you get Ri times C times Rj, and everything else stays the same. Okay. So what we have, you notice that these row operations are actually, so like I was like turning my hands and like showing the Rubik cubes and things like that, but these operations are actually coming from matrices. You can think of these operations as coming from the multiplying by matrices. Okay. Now, so let me define matrices of type 2, 3, and are called elementary matrices. Now, note that if E is an elementary matrix, then there exists another elementary matrix. Capital F, such that E times F equals F times E equals IM. Okay. So in this case, we call F as the inverse of E. Let's think about this thing a little bit. So before going into computation, so if you multiply by IM, okay, you multiply by IM, then you're not changing the system. Okay, good. And if you multiply by E, that means you're changing the system, you're doing something for some row operation. And then you multiply by F. After you multiply by E, then you're doing something else to the system, right? So this formula tells you this, whatever you're doing with F is actually undoing what you did with E. Okay. Okay, so that's kind of the inverse operation. Good. So actually, so that kind of gives you the motivation for this definition. And this is the inverse of a element of a group. That this is the definition. Okay. And now, so there is a notation for this. So in the case of integers or like real numbers, what is the inverse of 2? It's half, right? Yeah, so that's half. And you write as this is 2 to the minus 1. Okay. So the notation, write F as E inverse. Same notation. Okay. Good. Now let's see. So let me write. Let me give this thing as exercise. But call it exercise 5. This is easy one, but exercise 5. Let me call this thing exercise 5. Okay, so if you have elementary matrix, you can find a matrix that undo the no, if you have elementary matrix, you can find the inverse of that matrix. It is also elementary. Okay, and then the kind of the idea how you find it is like, for example, what would be the inverse of this matrix? So this matrix switches the rows I and j. Yeah, if you do it again, then you'd get back to identity, right? So you can verify that if this is matrix E, and if you take F to be this one, then you get the same one. Okay, when you multiply, you get the same thing. So in here, we take this matrix, and the inverse of this would be you replace lambda with 1 over lambda. Okay. And in here, if you multiply by C and add here, and then you multiply by minus C and add, that would undo this thing. Okay. Now, so all good now. And here you have I call this thing the inverse. Okay, so this would be a property of a group. So the if we have another matrix, let's call it F prime, such that E times F prime equals F prime times E equals IM, then this F should be equal to F prime. Okay. So what's happening here? I have written this, that F is the inverse. Okay. So when I write I'm telling that there is only one, right? And you can show this one. If you have another one, then both those should be equal. Okay. So let me prove this thing. So for example, F prime. Let's take something like this. F prime times E equals IN, and then I multiply by you multiply by F from both sides, so you have F prime E times F equals IN times F. Okay, and then so this would be F prime times E times F. IM times F is F. Okay, and now E times F is identity. Okay, and then F prime times identity, that's F prime. So this tells you that if you have this, you have F prime that does this thing, and it's actually unique. Inverse is unique. Okay. Now, when you see something in group theory, in something like this in matrices, you immediately ask the question like, is this little computation, is that a property of a group? Okay, because it looks like that's all that happened in here. So when you see computation like this, we're like, probably this has nothing to do with matrices. Maybe it has something to do with the, so let me write down the exercise 6. Let n dot be a monoid with identity. Monoids have identity, it's associated. Okay. The identity E. If A in M is invertible, then the inverse. Then let me write it in detail. Let m if there exists B and C in M such that A times B equals B times A equals identity, and A times C equals C times A is also equal to identity, then B equals C. So in other words, if you have the inverse, then it is unique. Okay. So that's kind of what you want to see. Like if you do something in matrices, but you kind of feel like, we never use like scalar multiplication, we never use addition. Probably it's a theorem about monoids. Okay? That's the spirit. Now, let's go back in here again. Now we do something very interesting. So we define, so we have, so we consider this guy. Consider, we call it like this. This is E. Call it F. So these are matrices E in M by N, M by M. Yeah, E is an elementary matrix. Okay. Now, so this F is a subset in here. Okay. Okay. So like you remember these elementary matrices, like you remember earlier, like you were saying, like we're doing this operation and then you're doing this and that, like you doing it with the hand, like in the case of the Rubik cube. But now we have like actual, so we have this guy, MNF. This is an algebra. This has everything in it. Okay, and now we found the kind of the basic operations that are responsible for when you solving linear equations. Okay, now we kind of located them like algebraically. Okay, there are just a bunch of elements in this algebra of matrices, right? And I was telling that now, he got dropped, but he'll come back. Any questions, Kisala? Aditya, are you there?
Yes, I have a bad
Oh,
internet
you
connection.
can
That's it.
come inside, right? I don't have to admit you. Okay. Now the question is, I mean, I was claiming earlier that these elementary row operations, they form a group. Like you were saying that we should be thinking those as a group, right? But question is like, is this a group? Under matrix multiplication. See it's not a group. Because if you do, you can take two elementary matrices and then you multiply them. That product might not be elementary matrix. Okay. So the answer is no. Right? And then the kind of the natural object to think about is actually you look at the finitely many products of these things. That's what you're doing actually, right? You apply one operation, then after the other one, and so on and so on. Right? So what you're doing, so we start with this system, and then you multiply with some elementary matrix. Okay. And then you do multiply with another elementary matrix. Okay. Meaning like, you're doing this and then okay. And I mean, you do it until this whole thing becomes a matrix in the reduced row echelon form. Okay. So maybe it's not F, maybe it is this type of products that we after. Okay. And so we consider proposition. So we consider G is of the form E1 times E2 times dot EK, where EI is in my set F equals. Okay. And we kind of, I mean, this is a product of K terms, and you think a product of zero terms is just the identity matrix. Okay. Now, and then G, which is inside here, is a group. So can I leave this thing as exercise? So let me, I'll leave this thing as exercise, but I'll tell you the idea. Okay, so this is exercise 7. So what you need to prove, closed, associative, identity, inverse, right? So the first one, so what's happening in here, so we have the, so we are looking at G with the matrix multiplication. And we know that the matrix multiplication is the closed operation in M by M matrices. You multiply two M by M matrices, you get M by M matrix. Okay, but now we are trying to use the same operation, but in a subset. Right? So this is where this closeness comes in. So we need to show that we take two matrices A and B in G, then the product A times B is also in G. Okay? In other words, that this product is a binary operation in the set G. Okay? So, and this is true because matrix A is going to be some product of K terms, and matrix B is going to be some product of, like, K prime terms, and then you have A times B. That's going to be like long sequence of terms, right? And it's going to be associative because matrix A is going to be a bunch of terms like this and so on, and you have like the associativity from the big matrices that's going to force the associativity for the G. Identity, because we know that I mentioned that this is the K terms, and we assume that when K equals 0, I mean, also you can think of when K equals 1, the identity matrix is like the case when lambda equals 1, which is included in here. Okay. And inverse is the interesting one. So the inverse, this is funny. Okay. So the inverse of this, we take A to be let me write it this way: E1, E2, ek. Okay. I mean, it doesn't matter which way you write. Now the inverse of this what is the matrix that you have to write here so that when you multiply these two things, you will get identity back. And if you think in terms of like row operations, we had some system, we apply E1, E2, and so on up to EK. Now you go back to the original system, right? So you have to undo things, but you have to undo it from the starting with the last thing you did. You cannot undo with the first thing. That's gonna like scramble things. Okay, so you have to undo things very carefully. So you have to do this EK inverse and so on, E1 inverse. Okay. And similarly, like when you prove the inverse of elements, you have to do this. Let's call this thing the B. So you have to show that B times A equals A times B equals identity. You can see that if you multiply this the other way around, you will still get the identity. Okay? So that means this thing is a group. Okay? And then again, we had the intuition from matrices, row reduction, and all that. But probably this is not a theorem in matrices. Okay. So this is what's happened in here. This is just a theorem in monoids. Okay. So you remember in a monoid, we don't even specify. It happens in a general monoid. We don't even specify what the operation is. As long as that operation satisfies these properties, this type of theorem should hold. Okay. So let me write down that theorem. So exercise 8. So what we had a monoid. Let M dot be a monoid. And let F be a subset of M. Be a set of invertible. Of M. Okay. And for our elementary matrices, we had the property that its inverse is also in the collection. Right? When I write it like this, then it's not. We had kind of somehow put that in there too. Okay. So our F from our like the row operations case, the set F was like close and inverse, meaning if you have element in F, then that inverse of that element was also in F. Okay, so you had to kind of fix that too. Then set G given by we call it A1 dot AM, where AI is in F, or AI inverse is in F. Yeah, call it K. Set G is a group. Yeah. Same. Okay. So the above proposition is this. When I write this thing, that's kind of take care of the inverses. In other words, I can put element in F or its inverse in here. Okay. So this is the kind of the abstract theorem of the what we had over there. Good. And this is what you. I mean, this is when you actually think about it. This the mathematics is the study of structures, and the mathematician should be somebody who can pick up the structure. Right? Let's say this is a story some engineer tells you about matrices, so like something very specific, and you need to be able to see the structure that's going on in there. Okay. Okay. No, 9. Uh, this one. So in here, what we did, we looked at like individual invertible elements, and then we considered they're like finite products, and then you show that those things form a group, right? How about we just consider all the invertible elements of a monoid, right? And does that form a group? That, right? So let M be a monoid, and I'd call it M tilde, set of elements in M such that A is invertible. Right. Then let this, then M delta under this is a group. So this one is actually it's going to be not that difficult. So the idea is like you consider like the problem with the monoid. It's like you don't have the property that every element is invertible. The monoid is closed, associative, and it has identity, and it's missing only one property to become a group. Okay, and this is telling you if you take a monoid and you consider all the invertible elements, that would form a group. Okay. Now in here, in other words, if we take M by M matrices over, let's say, R or C, you consider invertible elements, invertible matrices. That would be, we denote this thing by GLN. These are just the matrices in here. Let me call this thing A. Such that A is invertible. And so as it, I mean, by exercise 9, you get GLNF. This thing is a group. Because this is a monoid, and you're picking up all the invertible elements, that would be a group. Okay. Now the interesting thing is, so kind of it's a nice picture. So we have we have this guy, all the n by n matrices, and then you have this group. These are all the invertible matrices, right? And in here you have elementary matrices. Like E1 and so on, the various elementary matrices. And we showed that we can construct a group out of these guys, right? So which is like you take finite products of these things and then you construct a, let me see what this thing is. Yeah, that's I call this thing G. Okay. So the way we define this thing was just, you just say that, okay, consider all the invertible elements and so on. But this one is much more concrete. You're kind of actually constructing the elements in G. You start with things that you know, and then you multiply them, and then you build it up. Okay. Okay. It will be really nice if these two things are equal. And we're going to see this theme a lot, like you have like big object, and it's easy to define something from the, like, by specifying something and you get the object that you want. But it's a whole different story to be able to actually get hands on those objects. So actually, later we will show that this is actually true. We will show that actually G is equal to GLNF. In other words, any matrix, any invertible matrix can be written as a product of elementary matrices. Okay. Uh, so yeah, so this is the group that's responsible for the row operations. Okay. Yeah, maybe you can try this. It's okay. Exercise 10. Show that. No, let's not do it. I'll write exercise 10 later. Okay. Any questions? So this is like this path is okay, but it's like very narrow. Like we have these roads in yeah, Lord of the Rings, like tiny bridges and stuff. You can follow through this, and you won't get into any trouble. You can like go step by step. But yeah, but if you try to go in other ways, then you can be in trouble. Okay. Uh, any other questions? So we yeah, we will finish up the group action picture for the systems, and then we like finish the solving in by uh, in systems, and we discuss all the cases, no solutions, and so on and so on. And then we will jump into the book. Okay. Any questions? No. So there are office hours. So use it, okay? So and just come and if you have questions, always like try the questions, gather up the places you don't understand, and then you go ask. Okay? And especially when you go to the university, especially in US, you go to office hours. Okay? Okay? Uh, and like typically have people, yeah. typical, like, yeah, some people don't go to office hours, but it's very important that you go. Okay, that's like very good opportunity. Any other questions? Questions. This looks, I mean, it's abstract, but it's gonna get more and more concrete. And I mean, I understand, like, you don't have practice with those axioms, like the properties of groups, rings, and everything. So you like slowly prove things, and then you get used to it. Okay, and yeah. So let me stop the recording.